Alright, here we go. Lesson 7-1. We're starting a new chapter now. We're leaving some of the shapes behind. Not necessarily behind, we'll still be using them, but we're going to be getting more into algebra type stuff, looking at proportions and similarity of shapes, and we'll talk about how those two things relate and tie into each other. As we're looking at these, there are some terms that we need to bring back into our mind, and one is definitely proportion, and I'm sure you've heard of this term proportion before and used it, and the other one is a ratio. Every time I hear the word ratio, I think of rational, right? That's one of the first groups of numbers that you learn are the rational numbers. Anything that can be written as a fraction is a rational number. So therefore, essentially, a ratio is a fraction, right? So we're going to be dealing with lots of fractions, lots of ratios, lots of proportions as we get in here. Now, if we have two numbers, so here we have a and b, and obviously a and b are not numbers, but they represent some number in this case. And if we can say that a divided by b is equal to c divided by d, two other numbers, then we've got what we call a proportion, and we'll give it a firm definition in a minute here, but we essentially have a proportion. Now there's a lot that we can do with this if we say that a divided by b is equal to c divided by d. And one of the first things that you guys learn, and probably the one that's easiest to remember and most useful, is this idea of cross multiplication. Whenever you have an equal sign and you have a proportion where you have two ratios, you can cross multiply. So a crossed over multiplied by d is going to be equal to b crossing over multiplied by c. So you get this cross multiplication where AD is equal to BC. So they're just kind of giving you some of the properties and some of the things that you can conclude whenever you have a ratio like this. The other one, we know anytime that we have an equality, if there's an equal sign, we have an equality, and we can essentially do the same thing to both sides, and the equality will remain true. It will remain equal. So in this case, what they've done is they've taken the reciprocal. So notice here it's a over b, now they have b over a, so if we do that to the left, then we're also going to need to do that to the right-hand side as well. So b over a is also going to be equal to d over c, taking the reciprocal of both sides. And there's lots of other rearrangements. So if you have a over c, well, you can see kind of a pattern emerging over here. You're going to get b over d is going to be what it is equivalent to. So you can kind of follow the pattern that's going on here and get all of these different equalities. The reason that they're showing you these things is because at any point in time you may have some sort of proportion where you have a variable, and any one of these combinations may help you to isolate that variable, get it into the numerator so that you can solve. The last one is a little harder to see. So it's a plus b over b, and that one may not follow as much of a pattern, but you should still be able to see it. We started with a over b, now we're just adding the denominator b, so that should be equal to c over d, but then add the denominator here, so we get c plus d over d. Now again, that one's not quite as intuitive, so I thought if we kind of showed it in a little more detail, it might make some more sense. So I'm going to switch over. We've upgraded here. I'm going to switch over to my cam. And if you see how I have it written here, now I thought I could, use my hands and say, oh look, there's a thing and another thing, and but my hands aren't quite as pretty. I thought maybe it might be fun to introduce a little character. That's my friend Dixon. He just happens to be a pencil. Now, the benefit here is that my hands don't show a lot of emotion, whereas Dixon, if we make some sort of mistake, for example, if I were to say, hey Dixon, should I just go through this problem and not show any sort of work and just show an answer? No, that's bad. So he's going to tell us right away if something's going wrong. So, alright Dixon, let's make sure that we show all our work. We're going to show all of our calculations along the way. Does that make you feel better? Okay, he's back in better spirits. Alright, now if you look, here's what we had written before. A plus b over b is equal to c plus d over d. Now, if I were to split this up, notice we can separate these to a over b plus b over b. If we separate our fraction into two separate terms. And we can do the same thing over here. C over D plus D over D. Now, the really neat thing here is that B over B, if we divide something by itself, we just get 1. Right? We get 1. D over D, we also get 1. So if we rewrite this, if we look down here, if we rewrite this, we get A over B plus 1 is equal to C over D plus 1. Well, and if we have 1 and 1, we can just subtract 1 from both sides or eliminate those, and we're left with A over B equals C over D, which is what we started with, right? That was the original proportion. So we know if we can manipulate this to eventually get this, then we know that our original statement must have been true. Okay, as long as we can show that this is also equal to this. So, all right. Hopefully that made a little more sense of this last one here. So, some definitions as we continue on. Formal definition of a proportion is just a statement that two ratios are equal. Right? So we said we've got a ratio on the left, a ratio on the right. If we set them equal to each other, then that is officially a proportion. And we can see it written like this. You also may see it written like this, with a colon, right? Where A colon B is just the same as A over B. Right? Both are ratios, and both of these are proportions. Now, an extended proportion is when we have 3 or more ratios. So, for example, 6 over 24 is equal to 4 over 16, which is also equal to 1 over 4. You see these a lot when you're finishing a problem and you realize, oh, wait, that fraction can be reduced. And you divide everything by 2, and then you say, wait a second, that can be reduced again. And so then you divide once more. The thing that you have to be careful with extended proportions is that you don't end up abusing them, especially when we start getting into more and more detailed problems and you're having to show all of your work. You don't want to go equal sign crazy, because what I see a lot of people do is they do, this is equal to this, and then they go to move on to the next step, but they throw an equal sign in there. Maybe they have introduced a new variable or something like that, but they continue to throw equal signs in there, and so then you end up with a lot of statements that are not actually equivalent, and therefore the equal sign is not true. So just be careful with extended proportions. We talked about cross products, and I think most of you have experience with that, but the property itself, if we wanted to spell it out, says the product of the extremes of a proportion is equal to the product of the means. Now, we probably don't know these terms, right? The extremes and the means. They're not used a whole lot, except for in formal statements of properties and things like that in math, but it's always good to know these things even if we don't use them on a day-to-day basis. So when we look at a proportion like this, where we have A is to B as C is to D, the two in the middle are the means, and I always remember this by thinking, the mean is the average when you're talking about statistics, and so the average things are in the middle, right? The means are in the middle, or you could just think M and M. And then extremes, right? We can remember extremes because the extremes are on the outside, right? The extreme left and the extreme right. So the means are in the middle, the extremes are on the outside, and if we look at our cross product property, the product of the extremes is equal to the product of the means. So if we take A times D, that's going to be equal to B times C, which is exactly what we saw before in the box as we look above. Now, what do we use these things for? They come up a lot on the SATs. We're going to see them on our math tests, and you see proportions almost every year. Algebra, Algebra 2, they continue to pop up. But what are they really used for, right? What are they useful for? Well, one of the things is looking at a scale drawing, right? And so this is where we have everything in the drawing is proportional to the actual lengths. Now, if you're thinking about being an engineer, if you're thinking about being an architect, you're going to use these things all the time. Even business people, right? They have to do scale models of, if they're trying to develop a housing community, those sorts of things. So these scale drawings are going to come up quite a bit. Anytime you build a model car or a model airplane, or even just in art class when you're drawing something that doesn't actually fit on the page, right? If you're drawing someone's face, you're typically doing that to scale. You're not drawing it the same size as their actual face. Right? If you're drawing a building, if you're drawing, anything, for the most part, is going to be scaled to some extent. And oftentimes that can be the mark of some more sophisticated art, is when everything is proportional to what it would actually be. It makes it look much more realistic. And basically a scale is just the ratio of any length in a drawing to the corresponding actual length. They can be in different units. So that's one of the neat things that we'll see, is that you can have a scale, for example, on a map of 1 inch equals 1 mile. You don't have to convert that and say, well, 1 inch is equal to 0.0000 whatever miles. So when you have a scale, you can actually have the units being different as long as it's consistent. So we'll definitely be doing some hands-on stuff using scales and maybe making some scale models or scale drawings. Now, as we continue on with our first example, again, I always encourage you to, when we do the examples, to give it a shot on your own first. So pause the video, see if you can complete the problem, maybe do it in pencil so that you can erase if you mess something up, and then come back and you can continue watching the video to see how you did. Now, this example says that we have a scale model of a car, and it's 4 inches long. So this is, maybe a little bigger than the little Hot Wheels cars that you get as a kid. It says the actual car is 15 feet. So what is the ratio of the length of the model to the length of the car? It says write both measurements in the same unit. So they're going to actually have us convert in this sense, because they want the ratio. As soon as we say we want the ratio between the two things, then we need to put them into the same units. If they said they just want the scale, then we could just say 4 inches to 15 feet, and that would be our scale. But the ratio of their lengths, whenever they ask for the actual ratio, then we need to get into the same units. So here they're going to take 15 feet, and then they're going to multiply by 12 inches. There's 12 inches in a foot. To get the total number of inches in the actual car, 180. So then they substitute in for 15 feet. They say 180 inches instead. The units technically cancel, right? Ratios tend to not have units because the units will end up canceling. So we get 4 over 180, which can be reduced down to 1/45. So the ratio of the length of the scale model to the length of the car is 1 to 45. Now, the neat thing about this is that, notice they took the feet, the number of feet in the original car, and they converted to inches, but we could do it the other way around. So if we come down and look at this calculation, right, we've got 4 inches, and we're trying to figure out how many feet, so we're going to convert inches to feet instead. So last time, when we were converting feet to inches, we multiplied by 12. This time we're going to take 4 inches, and we're going to divide by 12 inches to get 1/3 of a foot, right? 4 inches is 1/3 of a foot. And then we can do the same calculation that we did before, right? We'll take the length of our model, we'll divide it by the length of our car, right? Our model's 4 inches, we said our car's 15 feet, but this time we're going to change inches to feet. So we can substitute 1/3 foot, so we have 1/3 of a foot over 15 feet, and if we reduce that, essentially multiplying the top and bottom by 3, we get 1 over 45, which is the same answer that we got when we did it the other way. So just a little side note in terms of being able to convert inches to feet or feet to inches. It doesn't really matter. The ratio will come out the same as long as you get the units to be equal before you take the actual ratio. All right, continuing on. Next example is fairly straightforward. They give us a proportion, right? A over 4 is equal to 12 over B, and then they want to know then B over 12 is going to be equal to what? So we can do this pretty manually, right? The instructions that they give here, they have you do the cross product first. So we know that A times B is going to be equal to 4 times 12, which is 48. And then they're going to try to solve for, essentially they're going to solve for B over 12. So they're going to first divide by 12A on both sides, which will eliminate the A over here and leave a 12. And so 48 over 12A is going to reduce down. We get 4 over A. Now, that's a lot of work, especially when on the first page in that box, they told us that if we start out with A over B is equal to C over D, and we take the reciprocal, B over A, well then we're going to take the reciprocal on the other side, D over C. So I would say there's really no need for all of this work. If we're taking 12 over B and we flip it to B over 12, then we're just going to take A over 4 and flip it to 4 over A. So much quicker, a lot more straightforward than how they explained it in the book. Moving on, now instead of having two variables, we're only going to have one. So we can continue to use our cross product property. Right, it's fairly straightforward. 5 times n, so we've got 5n over on this side, and then 2 times 35, which is going to be 70. And then we would just divide both sides by 5. Right? That way we isolate our n, and 70 divided by 5 is going to be 14. Now, there's another way to do this as well without necessarily doing cross product. Many of you that are fairly good at algebra or who have practiced algebra recently would recognize that we already have n in the numerator here. All we would have to do is multiply both sides by 35. Right? That would eliminate the 35 here, would just leave us with n, and we would get 35 times 2 over 5, which gives us 14. So that may be a quicker way if you are a little more skilled at geometry. If not, and it kind of confuses you, then just stick with what you know, right? Cross product will get you there. Just adds another step or two. Part B, the thing that I really want to stress here is, again, don't let additional variables, or when things don't look exactly the way that you're used to seeing them, don't let that fool you. You still have two ratios that are being set equal to each other. So you have a proportion. If you want to solve, we can do cross product, right? So we can use cross product, multiply, we get 3 times x, and then 2 times this whole quantity of x plus 1. So just remember when you do this, even though you have x plus 1 up here, you can still do cross product. But when you go to multiply this, don't forget that you have to distribute. So you would have 2 times x and 2 times 1 to give you 2x plus 2. So then when we subtract 2x from both sides, that just leaves us with x equals 2. As we go past the quick check problems here, again, I'll let you do those on your own. But I did want to mention, keep in mind that we do have different units here, right? So we've got inches and feet, so be very aware of that. And then part 2, they're just asking you, there are several different expressions that you could write. They just want you to write 2. So write 2 other ways that you could write this. For some help, you could look back at the very first box that we covered in this lesson. So now on for the final example. It says we're using proportions, and here we're looking at the example that we talked about before where we're talking about the scale on a map. They say 3.5 inches apart on a map, and that the scale is 1 inch equals 50 miles, and they want us to find the actual distance. So it says let D represent the actual distance. So if we have the map distance to the actual distance, that's a ratio, right? So we can say, well, 3.5 inches in map distance to D miles in actual distance, right? Because we don't know. That's what we're trying to find, D. And then we said the scale of the map is 1 inch to 50 miles. So whatever this is, our 3.5 inches to however many miles, is going to be the same scale as 1 inch to 50 miles. So we can set those equal to each other. Then from there, it's just a matter of cross multiplication and solving. In this case, we get D times 1, which is really nice because that's just D. So we get 50 times 3.5. When we do the other cross product, then it's just a matter of multiplication to get 175. So the cities are going to be 175 miles apart. And we've got the last couple quick check problems. Again, I'll let you do those on your own. The first 2 are fairly straightforward. Basic cross multiplication and then solve. The last one is going to be a little bit challenging, but really it's just example 4. They're just giving you new data, right? We're going to have 1 inches is 35 miles instead of 1 inches being 50 miles. And now they're going to give you the actual distance, and they want you to find how far the cities would be apart on the map. So you're going in the opposite direction. But really, same problem, same setup. You're just going to solve a little bit differently. So take a whack at those, and we will pick up with that whenever I return.